We will continue with this topic, which I'm calling sub-Nyquist frequency of arrival estimation, um, or in general, sub-Nyquist spectrum sensing. Okay, is my audio, video, screen, everything fine? Any issues anywhere? Okay, if not, then let me continue. So, what I'm going to consider has to do with compressive sensing also. We'll get into that. But before we do that, let me give you a very simple statement of the problem. And this is called a wideband spectrum sensing problem. And this is very relevant in today's world. And let me tell you why. The statement of the problem says that we have certain receiver, and that receiver sees a composite of many small narrowband signals, and they all have width of b hertz, but the overall range of frequencies that this narrowband signals occupy, which is denoted as f max, can be pretty large. Okay, so one diagram is shown here. So there are, let's say, 3 transmitters, and they are transmitting at f1, f2, f3, and they may be transmitting different signals. So their spectral shapes may all be different. And we have just one receiver, as it is shown here. And this receiver sees a signal which is a composite of all of these transmissions. And f max can be somewhere over here. And in general, this f max may be pretty large. And the reason why it may be pretty large is because over this spectral band, 0 to f max, the system operator may have provision for maybe 10,000 simultaneous transmitters. And if you want to put 10,000 of these little B bands, you obviously need f max, which is roughly at least about 10,000 times B. So compared to B, f max can be pretty large, much larger. Now, one of the advances that is being pursued in the context of next generation wireless systems is that you let this wide band to be opportunistically used. So if anybody wants to use a particular portion of this wide band, that user can start using it, but provided none of these important transmitters are already first occupying that particular frequency band. Because we obviously don't want to, for example, interfere with a base station signal, because this base station might be talking to multiple devices, and we don't want to disturb that, what is known as the transmission by the primary users. So in the context of this opportunistic spectrum access, there is kind of a hierarchy of the subscribers. One are called primary users. They are the VIPs, and they can start using the frequency band without any problem. Then the second tier users, sort of the second class citizens, are these secondary users or SUs, and they are free to use the spectrum in an opportunistic manner, but provided that particular range of the spectrum that they are going to start transmitting on is already first not occupied by the primary user. So obviously for this secondary user whose receiver is shown here, before it can start the communication link, it has to figure out where this F1, F2, F3 are. That is our frequency of arrival estimation problem. Because once it figures out what are these locations of F1, F2, F3, then it knows that other than those locations, I can start transmitting at the other areas of the frequency spectrum. Now, because this Fmax in general can be much larger than D, what is happening in today's world is that the analog to digital converter that this receiver would have is simply not sufficient, because this analog to digital converter can operate only at a certain maximum sampling rate, f of s. If you try to make f of s larger, as you have seen in lab 1, the sampling duration becomes smaller. And when the sampling duration starts becoming smaller and smaller and smaller, the electronic circuit cannot keep up with such very fine duration in the interval between two consecutive samples. Maybe if you use very expensive custom design analog to digital converter, maybe fine. You can maybe sample at this twice of Fmax, which is our Nyquist sample rate. But typically these receivers, the secondary users, their equipments are not expensive. And so they have ADC, which they have. I mean, you can't go and ask them to change their A to D converter. You can't say that you start using a higher sampling rate. So they are constrained to be using the type of A to D converter that they are built with. That A to D converter can handle B sample per second, but it cannot handle Fmax. Forget about it. So now if it cannot handle Fmax, meaning that it cannot satisfy the sample requirement of twice of Fmax, what is going to happen is that if such an A to D converter samples the incoming analog domain continuous time signal, that small f that we have studied in lab 1, remember the unique region of that small f is always from minus 0.5 to plus 0.5. But because this Fmax is very large, this F1, F2, F3, if I convert them into small f, they will become more than minus 0.5 to 0.5. They will sit outside of the base region of that normalized frequency small f. And we did this example, I think, towards the end of lab 1, that if I have, for example, this F1, which is outside of the base range, it will come and sit on top of F2, which is inside the base range. And that is going to just completely mess up our FOA problem. So that is the statement of the problem. How can we somehow recover the signals when we can sample only at B hertz, and when Fmax can be potentially much larger than B? And we cannot make any a priori assumption about the amplitude or the phase of these individual signals, because they are what they are. I mean, they are what the base stations are transmitting. We can't go and ask base station that, oh, don't transmit at this phase. Base station operators won't listen to us. Or even if they listen to us, the channel is going to mess up the transmitted phase, the wireless channel. And this again, if you have paid attention to that I think it was the last problem of that lab, you have seen that for a specific phase alignment between, for example, F1 and F3 or F1 and F2, if F1 comes and sits on top of F2, they can completely destructively cancel out, and you will not see anything there. The energy will be gone, right? So it seems like an impossible problem to solve. That was the hopefully the takeaway that you had in that last problem of lab 1, that if you try to do this, if you try to use a sampler which is operating at a sampling rate which is much smaller than the Nyquist rate, then your host is going to create terrible aliasing. Basically, there is going to be a lot of ambiguities in the frequency domain. And not only ambiguities, there's going to be a whole bunch of interfering effects. And so typically that is why people prefer to sample at rates which are at least Nyquist rate, or typically even above the Nyquist rate. But here we can't do it. This is the statement of the problem. We can't ask the secondary users to buy expensive samplers. So then it appears that this problem is not solvable. But that is where a neat idea was proposed, maybe more than 20 years back. Okay, so let me tell you this idea. The assumption behind this idea is that the secondary users cannot be asked to purchase a sampler which is operating at a very high rate, because that sampler will be super expensive, or maybe that sampler is outside of what today's technology can provide. Nobody has even come up with any such technology in the industry. But you can get the sampler which are operating at that B samples per second, and those samplers are pretty cheap. So you can get maybe 2 A to D converters. Maybe they're 500 rupees each. So fine. So you buy 2 of them, or maybe sometimes even 3, 4 of them. So the idea behind this paper is that instead of using one sampler, I will use 2 different samplers. They both are operating at same TS samples per second. TS, remember, is inverse of the bandwidth. So in between 2 samples, we have TS seconds of duration. Sorry, this is not samples per second. This is just seconds operating at TS sampling duration. The only thing that the authors of this paper have proposed is that the input to the second A to D converter, I will just shift it in time domain by some delay phi. Okay, so that is the only idea. And using that idea, they have somehow magically solved this impossible looking problem. So let us see that. So here are the 2 samplers. This is my incoming signal. Oh, and by the way, here in the incoming signal, I'm going to assume that there are only 2 signals present. Both are of frequency B hertz. And by the way, this is really not a frequency of arrival estimation problem yet. Okay, this paper is generally talking about how you can sample at a rate which is below the Nyquist rate and still recover the original signals. The frequency of arrival problem we will get to later on. This paper has led to that other paper that I'm describing. But here, the objective is that we want to recover the signals. And we are going to additionally assume that the center frequencies are known. Okay, so this is not frequency of arrival. This paper is solving this other problem of what if you are sampling at a rate below the Nyquist rate, aliasing happens, how we can still recover the original signals after they are severely aliased. So what they do is they take this x of t, which is a composite of two signals whose center frequencies are assumed to be known. And the same signal is passed through two branches. On this branch, they put an A to D converter. On the second branch, they put identical A to D converter. Both these A to D converters are operating at B samples per second, or sampling duration is 1 over B, as it is shown here. And so the output of those two samplers are the time domain sequences Y1 and Y2. And then the only change, the new thing that this paper does is it puts a delay on the second branch. Okay, now the only thing that is needed here is some clarity on the properties of Fourier transform. I'm assuming that you are all well aware with the properties of Fourier transform. In case if those properties are a little bit of a blur, what I suggest is that you go and revise, you just do a search on properties of Fourier transform, you'll get a lot of good web pages on that, or even any of the textbooks on signal processing that you may have, will have a very nice compilation of the properties of Fourier transform. Here we are going to make use of just one property of that Fourier transform. So what this paper has done is, it has taken this Y1 and Y2 and it has taken the Fourier transform. Now, if I take Fourier transform of Y1, what I'm going to get is the actual x of f. This is the original x of f. And then I'm going to, on top of this x of f, there will be an aliased x of f, which will come and sit on top of it. And that aliasing is exactly an integer multiple of f of s, where f of s in this case is nothing but capital B, because both of these samplers are operating at B samples per second. So the second term that you see here is nothing but that frequency fold over that is happening when you sample at B samples per second. This is identical to what we had done in the very first lecture, where we saw how the frequency becomes periodic. What this is saying is that the second band in which there is the second signal, it will come and sit on top of this original band. And this beta of f is just an integer. And that integer is specifying where that second band is. Remember, we are assuming that this incoming signal has only two narrow bands, both of B hertz. Maybe I should have written it here in the beginning. So if I take Fourier transform of Y1 of n, I'm going to get this. And this is coming simply from lab 1 that you have done. This addition is the aliasing induced addition that is happening. Okay, so nothing new here. For the second branch now, the same aliasing is going to happen, except because of this delay, there is going to be a phase shift in the frequency domain. And that phase shift, remember we have said earlier, is going to be proportional to the frequency difference. And the frequency difference is exactly this beta of f times b. Remember, beta of f is just an integer, which defines which particular band the second signal is residing in. And so now we have the same aliasing operation going on, except the second term, which has come and sit on top of our unaliased term, is having this frequency offset component added to it. So this is their main idea. Why this is the only thing that we need to do to solve this problem? Well, they said that this is essentially a system of linear equations. There are two equations and there are two unknowns, x of f and this other signal which is present at some other frequency, which is beta f times b away. I have two unknowns and I have two measurements. And I know exactly this phase coefficient because it depends on this phi term which I myself have introduced. So I can actually convert this two equations into a matrix vector equation. And then I just take inverse of that matrix to recover x and xf minus beta b from y1 and y2. And so when they did that, they were able to extract the original signal as if there was no aliasing present at all. This is a very simple matrix equation. You can write this in terms of a matrix. In fact, I will tell you that the first row of matrix is going to be just 1, 1. The second row of matrix is going to be 1. And this term, e to the power minus j2 pi beta of f, pb. That will be the 2 by 2 matrix. That 2 by 2 matrix is going to get multiplied by 2 by 1 vector x of f and x of f minus beta f times b. Then this is another vector y1f and y2f. So if I multiply the inverse of that 2 by 2 matrix with this y1 f and y2f, I get the original x of f and x of f minus beta of f back. And those are these two signals. I can take inverse Fourier transform and make them into filters. But if I don't do that, then I get this expressions. This G1f and G2f came out of that matrix inverse operation, which you can do on your own. Once you formulate the problem like this, getting these equations are very simple, very straightforward. And then once you get this operations, you just take inverse Fourier transform, and now you are back to time domain to perform this filtering operation, and you get the original x of t back. Or if you want x1 and x2, they are also present here. So you see that they have solved this impossible looking problem by using a very simple idea, which is that if I apply certain delay in the time domain, I get a phase shift in the frequency domain. And it is this phase shift that allowed them to define this matrix, which is invertible. And so now, because of that, this is the overall system diagram. I have two signals. I sampled them in sub-Nyquist domain. And because of that, the copies of this other signal came and sat on top of my first signal, which is in blue. One would have thought that this is a unsolvable problem. In a way, it is unsolvable if you are using only one branch. But this researchers said innovatively that there is no reason to say that we can use only one branch, because the A to D converter operating at this small beta B samples per second are pretty cheap. They can be purchased in multiplicity. So we just put another A to D converter, and by applying a small delay to the input to that second A to D converter, we can actually obtain our original signal back. Okay, so this is the main idea that was presented in a paper, as I said, in I think late 90s. And I'll keep this paper on our Google Classroom so you can take a look at it. Now I'm going to go to another paper. Yes, I'm going to, so this few slides came from these two papers. By the way, this technique is called periodic non-uniform sampling. It was defined by Lean and Vaidyanathan in this paper, which was written in 1998. And this main technique has been described by another paper by Mishali and Elder in IEEE Signal Processing Magazine in 2011. And the figures that I have shown are taken from this paper. But the idea came from this PNS paper. Okay, now I'm going to maybe over next 10 minutes or so, I'm going to get into an extension of this idea. Okay, so I'm now projecting one page of this other paper that I wanted to show to you. Are you able to see this page? It's a paper by Mishali and Elder. The title of the paper is Blind Multiband Signal Reconstruction. This paper is an advancement of the idea that was in that periodic non-uniform sampling PNS paper by Lean and Vedianath. The reason why it is an advancement is because in that PNS paper, remember, the assumption was that the center frequencies are known. And they were just interested in getting the original signal extracted by using samplers which are operating at a much smaller sampling rate. The reason I say that the center frequencies are known in that other paper is because that beta of f was known. If you don't know beta of f, then you can't do that technique that was described just now. What this paper by Mishali and Elder is doing is it is getting rid of even that knowledge. It is saying that what if I don't know the frequency of the incoming signals? That is that primary user, secondary user opportunistic spectrum access problem that I described just a while ago. Obviously, in that case, if secondary users, in that case, the secondary user would not know what the primary user signal frequencies are because secondary users are not part of the primary user system. And so there is no way that secondary users can have knowledge of what these primary users are doing. They are kind of opportunistically sneaking in and using the unused spectral band. So now this is a problem that is becoming more recent. And so I think this paper is also relatively more recent. It's probably published in 2009. So we have jumped about 10 years forward. Okay, coming from that other paper, we have jumped about 10 years forward. From 1998, we are down to 2009. Okay, so I had that particular page which I wanted to show you. So what this authors are doing is, as I was saying, they took that Lean and Vaidyanathan's idea and they ran with it. That is the resourcefulness that is required to do the type of advanced research that you all are engaged in. So what they said is that first of all, because there may be more than two simultaneous signals, I will need not just two A to D converters operating at B samples per second, but I will need a total of small p of them. So uh, they have actually a bank of such multiple A to D converters. Let me see if that diagram is somewhere shown here. By the way, this is the same diagram that I had shown to you at the start of that. Okay, so apparently not. This paper doesn't have a diagram like that. Maybe let me try to see if okay, yeah. So this paper is kind of showing what I was saying earlier. This is the incoming signal, which is wideband. It has multiple narrowband components whose frequency we don't know, and our objective is to estimate their frequencies. Lean and Vaidyanathan paper was processing this X of t using two parallel banks, where they had low rate sampler on each of these two banks. Here we have total of capital N parallel banks. The idea is still remaining the same. As you go from one paper to the other, the problem is that the notations keep on changing. So in this paper, they are saying that there is a total of small p such parallel hardware chains. So they have asked for small p A to D converters. But they have said that all of these A to D converters can be pretty low rate. They are pretty cheap devices. And just like what Lean and Vaidyanathan were doing, on each of this A to D converter, they introduce a delay, which is this small c of I. Remember in Lean and Vaidyanathan, that PNS paper, the c of I was denoted as phi. It's exactly the same thing, a different notation. So they have multiple A to D converter, and at the input to each converter, they delay by the incoming signal by a different amount. And then that delayed signal they pass through the A to D converter, which is operating at the inverse of the narrowband bandwidth. And so what they have said is that if I take the output of the A to D converter, then it can be written as this summation. This capital L was 2 in Lin and Vaidyanathan paper because they are considering only two users. I mean, two bands, two narrow bands. Here they are considering up to capital L narrow bands. And so that aliasing happens in an L-fold manner. A total of L different narrow bands kind of come and sit on top of each other. And that addition is what is shown by this equation 18. If they were not doing this delay staggering on different branches, then this first term will not be there. The aliasing will be happening as shown by this capital X, which is the Fourier transform of the input signal. It will just get added up in an L-fold manner. The only thing that they have done, which is exactly same as what Lin and Vaidyanathan were doing, they managed to sneak in this complex exponential phase offset. And just as in Lin and Vaidyanathan's paper, you see that this phase term is exactly proportional to C of I. In Lin and Vaidyanathan's paper, it was proportional to phi, because the C was denoted as phi. So this equation 18, they have just pretty much borrowed the same idea that was there in that PNS paper, except they have extended to a total of capital L different narrowbands. And then what they get is this Elias signal, X, capital X, CO5. And in a pictorial sense, this is how it looks like. Let's say there is a wide band whose total range is 0 to 1 over t. In that other notation, we call this 1 over t to be F max. There are 3 narrowband signals. And when you sample this wideband at a small sample rate, the only unique range is minus 0.5 to 0.5. And all of this signals will kind of get folded over because of the aliasing. And so that folding over is shown here. This is how these different signals are folding over. This little part is this one. The remaining part of the red is this. And then for the blue, this type of folding is happening. This yellow triangle is sneaking in exactly in its own shape. What they have shown, and this is again same as Vaidyanathan's paper, is that this aliased spectrum can be written as inner product of this phasor term, which is in our control because we can define this CO5. And the CO5s are the delays on different parallel branches that I was going to. And then this X of F terms, which they have collected in this vector. So again, exactly same as that PNS paper, but now they have a linear algebra form, which is this form. In PNS paper, this A was a 2 cross 2 matrix. Remember that. It was 1, 1, 1 and e to the power j 2 pi phi times b times that beta of f. Here, that matrix became bigger. And the individual terms of this A matrix came from this exponential term. But the final equation looks a lot like Vaidyanathan's paper. But there is one fundamental difference, which is that the authors make no assumption about the knowledge of where X of F has signal and where it does not. Remember, there are going to be many elements of X of F. This is showing X of F. There are going to be many elements of X of F without any signal. For example, this band doesn't have any signal. So that is where the idea of compressive sensing comes in. What these authors have said is that if and only if this X of F is sparse, meaning that these blues and reds are very small compared to the length of this X of F. Basically, this X of F is mostly filled up with zeros and only few non-zeros. Then this linear algebraic equation can be solved. And the authors have used an algorithm which is known as orthogonal matching pursuit algorithm. But there are other algorithms also possible. And once you invert this equation, because you know A, you know Y is the output of those chains that we were looking at. This outputs form Y's. This P0, P1, Pm, this collectively, this entire process defines this exponential functions, and ultimately those exponential terms get into this A matrix. So Y and A we know, but X we don't know. The reason why it is called compressive spectrum sensing is because X typically is very, very big vector. It may have, let's say the size could be 10,000 cross 1. We cannot put 10,000 A to D converters. So maybe over here we may put only 100 chains. So there may be only 100 such parallel chains. And so now this Y is only 100 cross 1. This is 10,000 cross 1. And so this A matrix is 100 cross 10,000. The power of this OMP algorithm, orthogonal matching pursuit algorithm, is that in this underdetermined system of linear equations, which is what this equation 20 is, the number of measurements y of f is much smaller than the number of unknowns, which is 10,000. This x of f will be 10,000 cross 1. So typically such underdetermined system of equation is not solvable. But what this compressive sensing algorithm does is it says that under the constraint that x is sparse, meaning is it has only few non-zero elements, all the others are zeros. In the system concept, it is as if there are only few primary users. There are only, let us say, few base stations that are active at a time. And a lot of this frequency axis is empty. Then compressive sensing can help us recover this x of f from y of f. Okay, I thought I saw a question. Let me just take a look at it. Okay, I think, let me see. Now my chat window is not there. I think I saw a flash. Did somebody ask any question?
Yes, sir.
Okay, yes, Divya.
Sir, I wanted to ask, like, depending on the sparsity of X, so if K is the sparsity of X, then do we have K ADCs at the in the like, at the input?
Yeah, excellent, excellent point. Yes. So if suppose there are 3 active users in this X of f, meaning 3 elements out of 10,000 are non-zero, remaining all of them are zeros, then generally you need 3 hardware chains. Instead of 3, if you have 100, then you need 100 hardware chains. But you don't need 10,000 of them. So the benefit of this compressive sensing is realized because instead of needing so many different A to D converters, you can get by with using only a few. And how many you need is determined exactly like what you are saying. It depends on the sparsity level of this X of f.
Okay.
Okay, so maybe I'll just take 5 more minutes. This is a paper that is further extension of that Vishali and Elders paper, and this came in 2012. So we are moving forward. We are coming closer to 2020. In fact, I can show you a paper that is written in April of 2020, which is an extension of this paper. So, but well, we will not get there. But this is the paper where they have taken the same idea of Michelin Elder. They have converted those CO5s into this specific coefficients, but ultimately they are still considering the same matrix equation. Let us see if they have it somewhere written down. There is some math which we don't need to get into too much, but the underlying idea is exactly the same. Well, specifically called out that matrix. Okay, I don't see that. Yeah, here it is. This capital C matrix here is same as capital A matrix of Michali and Elder's paper. This y of f is equal to A times x of f. This y of k is equal to c times x of k. Okay, they are writing this equation of Michali and Elder, equation 20, which is in frequency domain. The same equation they are writing in the time domain. The matrix C doesn't change. But now I'm going to show to you how this paper took the same basic idea and they did this autocorrelation sequence estimation. Remember, if I want to estimate the autocorrelation sequence of x of t, then I will have to sample it at Nyquist rate. If I sample it at rates below Nyquist, then I will have aliasing problem. And with that aliasing problem, if I estimate autocorrelation sequence, that is going to be a garbage. I won't know. I won't be able to make use of that autocorrelation sequence. The problem they are considering is same problem. They want to estimate FOA, frequency of arrival. But in order to estimate FOA, they are saying that we will constrain ourselves, we will tie our hands, and we will use samplers which are operating at a much smaller sampling rate of B samples per second, meaning that we will let aliasing happen. But we will still introduce the same delays, CO5s, that this paper by Michali and Elder is introducing. And therefore, we will get the same equation, y is equal to A times x. And now they are saying that we won't even use OMP algorithm. We won't use any of the compressive sensing. In fact, this paper is an advance on that Michali and Elder's paper, because they are saying somewhere that even the sparsity is not required. Somewhere they say.
But in the abstract.
Okay, so Joel has seen this paper. So somewhere they are saying that even the sparsity assumption is not required. They have said it somewhere here also in one of these paragraphs, but let us not get to it. So remember, they want to estimate the autocorrelation sequence of x of t. And that autocorrelation sequence they want to estimate as if x of t is sampled at a Nyquist rate of that f max, which is huge, 10,000 times b, which is not feasible in today's technology. So they are just collecting samples, this y0, y1, y of m minus 1. Now they have total of m parallel chains. They are collecting these samples which are all collected at a very small sample rate of b samples per second. What they have done is they calculate the autocorrelation sequence and cross correlation sequence of these y's. This they can do. They can not only get autocorrelation, which is yi of L times yi of L minus k. This is exactly the same equation that we had in one of our slides. So that they can do, but not only that, they can also do cross correlation, yi with y of j. Obviously, they won't be able to perform this expectation, so they will replace expectation by averaging, just the way that we were doing. But once they do that, they get an estimate of this auto and cross correlation sequence, ry, yj, with some delay lag k. In our formulation, I think this k was called L, but the concept is exactly identical. By using some very simple math that I know all of you can do very easily, this is some very basic math, just high school math. What they have shown is that this cross correlation sequence that they can compute, it can be written like this. This ry is what they are computing, and they have see this actually is going to be a matrix because it's a function of not only k but also I and j. So you'll get actually a matrix instead of a vector. Typically, the autocorrelation sequence is a vector. But here, I mean, if you consider only one branch and perform autocorrelation calculation in that, then you'll get a vector. That vector will be indexed by k. But as because you are doing here the complete auto plus cross correlation, you're going to get a matrix. So somewhere down below here, they are converting that matrix into a vector. Basically, they are dumping all of the columns of that vector one after another and making it to be a big tall matrix. And that is what they're calling R of y. What they have shown is that this R of y which they can get is this matrix R of C. And R of C is a matrix of the autocorrelations of this C's, C coefficients. But these C's are coming from the delays that they themselves have introduced. Remember, these terms are the C terms. And so because it is entirely under their control, they can calculate these entities, the auto and cross correlation among these C factors. So they have converted the problem of estimating R of X in the sub-Nyquist domain as the problem of solving this linear equation, equation 10, where R of Y they can calculate using this equation 3. R of C, this matrix R of C they can calculate using equation 5. And R of X is the unknown that they want to estimate. Because remember, once they estimate R of X, they will that is exactly identical to estimating power spectral density. And once they know the power spectral density, they will just look at the peak and they will figure out where are the primary users. So all they need to do is solve this equation. And there are linear algebraic solvers for that. There is something called pseudo inverse, which they can use to solve that equation. Even more, something that you will be able to relate is that they have written this y as c times x, which is as I was saying, same as this equation 20 of this Michalis paper. And then what they've done is they've taken autocorrelation matrix of R of y, and they got this equation number 25. This equation 25 should ring a bell in you. This is same as the autocorrelation function of the output of the DFT variables that we had in one of our slides. Except there is no noise term present here. We had this type of entity plus sigma u squared times identity matrix. That noise is actually folded into R of X. But otherwise, this equation 25 is very much like what we were looking at. Okay, so this is where they vectorize this matrix R of y. Basically, in order to apply pseudo inverse, they have to convert this into a vector. So all they do is stack one column of this matrix up on top of the other, and so it becomes a tall vector. That is this R of y. And when they do that, they are saying that this left-hand side also becomes vectorized. And this equation 26 is back to being the same equation 10. Conceptually, it is same. Here in equation 26, R of y is known, or it is measured. This huge matrix, C conjugate Kronecker times C, is also known to them because individual terms of C matrix are known to them. And so using this and this, applying pseudo inverse of C conjugate Kronecker dot product with C, they can get the estimate of R of x. Once they get estimate of R of x, it's a simple matter to get autocorrelation sequence of the input signal itself. And the last bullet of the last slide that we were looking at said, once you get autocorrelation sequence of R of x, you have solved the problem of frequency of arrival estimation, because that is giving you the same information as power spectral density. This is where I will stop today, but the point that I wish to emphasize to you is that the original idea was very simple, but those who thought of it were very smart also, I would have to say, because otherwise maybe someone like me would have said, no, when aliasing happens, the signal is corrupted, you can't recover. They said that no, it is a solvable problem if you relax the hardware requirements a little bit. That original idea in that 1998 paper was taken forward by Michali and Elder in 2009, and Michali's idea was taken forward in 2012 by this name is pretty strange, Ariananda and Gerd Lees. I think they are probably from Greece. And they have solved this problem. There is a lot of math here, and I think Joel is looking at some of this math. But the only prerequisite that you need to know from this signal processing perspective is what we have covered in our slides. These authors, other than those prerequisites and their knowledge of the properties of Fourier transform, they didn't make use of any other mathematics. No real calculus, complex calculus, no integration, nothing fancy, no abstract algebra. So it's using something very basic. They have developed something which is very relevant and very pertinent in the context of next generation wireless systems. Okay, so I'll put some of these papers on our shared folder, and you can take a little bit of a deeper look at that. You don't want to get overwhelmed by the equations. Rather, you want to understand their main idea. They are just kind of pounding on. They are kind of dumping hammer on the same idea over and over. And once you get that idea, then you can maybe come up with your own novelty, which will further expand this paper. As I've said, there are extensions of this paper that have been written as recently as May of this year. So, okay, so I will stop here.